Hello, everyone. Thanks for joining us. It's great to see you all. As you all know, I'm Greg Finley, Director of Learning for Action here at Terra.2. Our speaker today is Alison Smart. Alison works with leaders across science, design, technology, business, and culture to develop useful, resonant, and beautiful climate change tools and resources. Through her role as Executive Director at Probable Futures, a non-commercial climate literacy initiative, she helps people across different industries and geographies build their capacities to evaluate and address climate risk. Prior to Probable Futures, she served as Vice President for the Woodwell Climate Research Center. Alison came to climate change communications after spending the earlier part of her career in the arts, and she believes that not only do we all have the capability to understand the science and context of climate change, but that everyone will need that understanding as we navigate through a changing climate in a changing world. Many of you will have looked at Probable Futures tools in your labs just yesterday, and we're very excited to have Alison with us today. So Alison, thanks so much, and take it away.
Awesome. Hello, beautiful people. Thank you so much for having me here with you today. I love giving talks to these groups. I always get so much energy out of it. So thank you for allowing me to do this. I'd love to just get a sense of where everyone is. So while I start sharing my screen, maybe you could just drop in the chat where you are in the world. And I'll get started here. All right, so we've got some Vermont, Colorado, Ireland, UK, Seattle, Bay Area, Hawaii. I had a dream about Hawaii last night, and very randomly. So Italy, Toronto, India, awesome. So excited to be able to connect with so many people from around the world, from where I am in Dartmouth, Massachusetts. So kind of on the coast of Massachusetts near Cape Cod. So I will get started. Greg mentioned that I spend a lot of my time talking to people about climate change, and in particular talking to leaders of different communities about climate change. And one of the things that we have learned in that time is that many of these people are thinking about climate change for the first time, or sometimes it's part of their job or part of their company's role when it wasn't previously. And the most important thing that we've learned is that every person, every leader, no matter where they are in the world or what kind of community they're a part of or that they lead, can benefit from this very same orientation on the fundamentals of climate change. And they can use similar frameworks for taking action on resiliency, adaptation, and mitigation. And so that framework is what I'm going to share with you today. It has three aspects to it: context, preparation, and imagination. We'll get started with the first and most fundamental, which is context. Because what is the context for climate change when the Earth is 4.5 billion years old, and our human species is much younger than that, and our civilization is much younger still? So how should we think about the importance of a changing climate today, in this moment in time? So we're going to start by examining this question and traveling back into the history of our climate and our species to find the answer. And let's start with our civilization, because before the climate started to change in the 20th and 21st centuries, we were the beneficiaries of an unusually stable climate, one where the global average temperature, and by extension the climate, was largely unchanged for about 12,000 years. And we know this thanks to climate science. So here we're looking at a graph of the history of the global average temperature. And the graph starts at the dawn of civilization about 12,000 years ago in 10,000 BCE, before Common Era. The way to understand this graph is it compares the global average temperature of each of these years to that of the late 19th century. So the closer the data point is to zero, the more stable the global average temperature was. So we can see here that during the time of civilization, the global average temperature barely even fluctuated a degree. So we'll call this green band here, the civilization temperature band. And this stability in the climate allowed humans to do things like practice agriculture and settle into permanent communities where we know that we could keep on living a comfortable life, and eventually building up things like governments and economies and schools and corporations, eventually to this really complex society that we live in today. And it happened to be that the climate wasn't just stable, it was actually perfect for humans. There were large expanses of temperate land where we could settle. There were stable seasonal patterns all over the world. So even people that settled in the Arctic, for example, could depend on the patterns of the climate and build their civilizations around that. So for another example, people who lived in monsoon regions, it doesn't mean that that the climate was always stable within the year, but there were these year-to-year patterns that communities could build their societies around. And importantly, nowhere on Earth was it too hot for the human body to survive and live. So it begs the question, why didn't humans settle before 10,000 BCE? And conversely, it's because the climate wasn't stable. So our earliest ancestors emerged in Africa around 200,000 years ago. But for about 180,000 of the years that we've been in existence on this planet, we were a nomadic hunting and gathering species. And looking at this chart gives us a sense for why the climate changed dramatically in those 180,000 years. So we'll call this blue band here the human existence temperature band, because humans have never experienced global average temperatures outside of this band. And so a changing climate at this magnitude was just not conducive to settling into one place. And then if we go back even farther into history, we can see that a stable climate is certainly not guaranteed. The Earth has actually been much hotter than it has been during human existence, and so hot that only reptiles like dinosaurs and insects could live above water back 70, 80, 90 million years ago. This was not a climate where large mammals like humans could live. But I'll direct your attention toward the right-hand side of the graph here, where we've added on recent temperature observations and then also climate model data from here. And what we see is that we are already breaking out of this civilization temperature band that we've known for the past 12,000 years. And if we continue on the same trajectory, we'll be breaking out of that human existence temperature band well before the end of the century. So this graph helps us see that climate change isn't just about warmer temperatures. It's about losing stability. It's about the fact that maintaining civilization in a changing climate is unprecedented for our species. It's a paradigm shift. So in order to navigate through these unprecedented conditions, we're going to need a lot of new skills. We're not going to be able to fall back on all of the same skills and tools that we have used in that stable climate. And one of the most important, we think, is something that we call climate awareness. And we need this climate awareness because there are assumptions of a stable climate hidden in every aspect of our society, our food systems, our infrastructure, our homes, and even our cultural practices, many of which are built upon the patterns of a stable climate. So here are some examples. Things like storm sewers are designed for specific amounts of precipitation in certain places. And power systems are meant to withstand certain max temperatures or load factors. Residences in many places in the world are meant to keep heat in rather than keep it out. Our grades of asphalt on our streets are different depending on where you are in your latitude. And all agriculture, whether it's irrigated or not, is dependent on steady precipitation. And so these are some of the obvious ones, but every community, every sector every industry has assumed climate stability in different ways, and climate awareness can help us start to kind of peel away at those assumptions and recognize where those assumptions will turn into vulnerabilities in a changing climate and where it'll turn into life just simply being different. So our job from here is to keep this foundation, the stable climate, from deteriorating any further, and that's mitigation. And then our job is to keep the things above it as resilient and as functional as possible, and that's adaptation. So fortunately, because of climate science, we know a lot about how the climate will change at each increment of warming. And that gives us the opportunity to think ahead and prepare so we can do those things that I just showed you on that last slide, adaptation and mitigation. And we can start using the science that we have at hand to plan for the warming that is assured and motivate society to avoid further levels of warming that would bring further destabilization. And to do that, we need the science, of course, but we need it to be presented in a way that resonates with people who are making decisions in the real world. And that science needs to answer real world questions. And that was the impetus for starting Probable Futures, which the genesis of it started when I was vice president of the Woodwell Climate Research Center, seen here. And the initiative was founded by Spencer Glendon. He was also associated with Woodwell Climate Research Center at the time, and it grew out of a collaboration that we were a part of there. And so I was recruited to Woodwell not because I had a science background, but because I had a storytelling background. So at the time, Woodwell's climate scientists were really looking for help from non-scientists like me and like Spencer, people who could present their science in a way so that others could meaningfully use it. So what we did is we intentionally started building a team of generalists like us, people who could help bridge the gap between climate science and other aspects of culture and society. It's one of the reasons that I love talking to this group so much, because everyone here is in the process of becoming a bridge builder in this way. But at the time, we were used to seeing climate science that was like this, presented like this, and like this, and like this. And this is not to throw shade on any of this information. This is critical science that people have spent years developing, and it's really important information, but it certainly doesn't send the signal that it's for me as a non-scientist, and it doesn't help me really viscerally understand the nature of what we will be facing. So we set out to build a resource that would show how useful and intuitive and personal climate science could be. And we would do that with Woodwell Climate as our partner. And of course, we knew that the heart of this initiative would be around maps. Maps are intuitive, they're interesting, and they're also really useful. We use them every day. And so we built Probable Futures using this very familiar tool in order to empower people to see climate change through their own lens. So what we do at Probable Futures is we make data about the most fundamental first order impacts of climate change, temperature, precipitation, drought, without any additional analysis on top. And this is because climate change is going to mean very different things to different communities. So let's take, for example, this map of days above 32 degrees Celsius or 90 degrees Fahrenheit, just outside of Bogota. So the map on the left here is showing a past climate. So this particular region could expect in a past climate, something in that stable climate, something like 118 days on average above this temperature threshold. In a cooler year or a 10th percentile year, something like 49 days. And in a hot year or a 90th percentile year, something like 214 days. So fast forward to 3 degrees of warming, climate models project that now this place will experience something like an additional 110 days above 32 degrees Celsius or 90 degrees Fahrenheit. But really, this community is best positioned to understand what this would mean for them, what it means for their infrastructure, for their industries, for their schools. Maybe they're really interested in something that's happening in a different part of the world or a different part of the region that they're really connected to economically or in some other way. So no one is going to be able to parachute in and provide all of the answers about impacts of climate change in every place around the world. What we can do is we can give people good tools, prompt relevant questions, and have a framework for thinking through the impacts. We can empower these communities. So I'm going to run through a few maps here just to give you a big picture sense of the changing climate at future increments of warming and to orient you to the maps here. I know you've done a little bit of work with them. And then we'll dig into some more specific places and examine them. So the map that we're looking at, Okay, so the map that we're looking at here is a map of the number of days above 35 degrees Celsius or 95 degrees Fahrenheit. And all of Probable Futures maps are organized around these warming scenarios that you see here that I'm sure that you are familiar with at this point. Each one starts with this past climate. This past climate represents the time period of 1971 to 2000. It's the earliest time that these models can produce output. And at that time, the Earth had already warmed about a half a degree Celsius beyond pre-industrial temperatures. So we use this 0.5 degrees as a proxy for the past stable climate. It's our baseline, if you will. And then the climate models then project what these variables will look like at different increments of warming. So you can see the key down here, the colors coordinate to the number of days above this threshold per year. And this key will change as we go through different climate variables. So just keep your eye on that. And I'll move you through the warming scenarios here. So, and I want you to look at how the reds and the pinks expand in the equatorial regions, and the blues and the greens in the northern latitudes and the southern latitudes move towards the poles. So we'll start with this past climate scenario of 0.5 degrees, 1 degree of warming, which is really kind of the world that we're in now. So the Earth has already warmed 1.2 degrees past pre-industrial temperatures, 1.5, 2, 2.5, and 3. I'll go through that one more time just to see how the dynamics of the data. 1.5, 2, 2.5, and 3. So moving on to wet bulb temperature, which is a really important aspect of increasing heat. I mentioned earlier in this talk that nowhere on Earth was it too hot for the human body. Well, there are places on Earth that are really hot, that reach very high temperatures, but they generally tend to be dry places. And what really matters for human physiology, we're big mammals, we need to offload heat. We do that by sweating, and the air around us needs to be able to accept that sweat. So the combination of heat and humidity, which we call wet bulb temperature, is a really important aspect of increasing heat as the climate changes. So the way to understand wet bulb temperature is it means this temperature and 100% humidity. So we're looking at a map of 28 degrees Celsius, days above 28 degrees Celsius, and 100% humidity. There are other temperature and humidity combinations that could get you to 28 degrees wet bulb. But I find it easier just to think about it as 28 degrees and 100% humidity. And so you're looking at a map here that really has mostly gray on it. And if you look at the key, gray represents 0. So in most places in the world, this particular threshold of temperature and humidity just doesn't happen. And in the places where it does generally happen in this past climate, it happens something like 1 to 3 days a year, 4 to 7 days a year. And then in some parts of Southeast Asia, they're used to seeing these temperatures more frequently. So move through the warming scenarios here. 1, 1.5, 2, 2.5, and 3. I'll show you that again because these are really significant changes happening in many places throughout the world. 1.5, 2, 2.5, and 3. I'll keep moving here. Let's take a look at drought. So this map depicts the probability for a continuous 12-month period where the conditions for extreme drought in that place are met. So in this map, it's important to recognize that drought is relative. The term drought is relative to the climate of that place. Drought itself, the concept is really kind of a result of having climate stability. Drought is supposed to represent an aberration of a historical heat and precipitation pattern. So in this past climate scenario, an extreme drought for any given place is considered an event that happened around 5% of the time. So that's why in this baseline, you see only gray here, because every place extreme drought is something that would happen 5% of the time. So what we're going to do is we're going to take that drought and see how much more likely it is in each given place at each climate scenario. So for instance, a drought in the Amazon is going to look completely different than a drought in Delhi, but this map takes that into consideration. So 1 degree of warming, so we can already see these kind of pea green colors. A lot of these places that experience this extreme drought 5% of the time now are seeing it something like, over 10% of the time, up to 20% of the time. 1.5, 2, 2.5, and 3. So as we look at these really dark colors, or these bright orange and the dark red, is over 50% of the time. And what this really means is that this is a new climate regime for that place. If there's a past drought that happened, 5% of the time, now you can expect it something like every other year. That's not drought anymore. That is a new climate for that place. Moving on to precipitation. So here we have a map of the frequency of a rare storm, which is often referred to as a 1 in 100-year storm. Again, this is a concept that is really produced by having climate stability, because a 1 in 100-year storm is really just a storm with a 1% chance of happening at any given time. But we called it a 1 in 100-year storm because in a stable climate, every 100 years is essentially the same. So this map shows how the frequency of this storm will increase in a warming world. So the way to understand this map, the darker the blue, the more likely that 1% chance storm is. So 1.5, 2, 2.5, and 3. So you can see most places in the world that rare storm is more likely. Some places it's 2 times as likely, 3, 4, 5 or more times as likely. I mean, you may think that this is kind of conflicting with the map that I showed you earlier, because there are a lot of places in the world are having more frequent droughts, but that is one of the key aspects of precipitation in a changing climate, is that we will have prolonged dry periods, more prolonged dry periods, and when the rains come, they will tend to be heavier and wetter. So we're seeing the range of possibilities increase when before it fit within these very stable seasonal patterns. All right, so now let's drill into some specific places and ask, how can we actually use this data to think ahead and to prepare? So I'm going to look at Paris here, and we're going to look at a measure of heat, so the 10 hottest days in a given year. And you might say, okay, Paris is in a place that I think of as, having a vulnerability to extreme heat. And in a way, that's why we need to look at it and think about it. Paris is a very old city. It's a very wealthy city. And so it was designed around very mild, very specific mild temperatures. And so as the climate changes, we're going to be moving out of those temperature ranges. And Paris's infrastructure isn't necessarily prepared for that. So for example, less than 5% of residences in France have air conditioning. So this is a place that is not used to dealing with extreme heat that now will have to deal with it going forward. So we're looking at this 10 hottest days. The way to understand this, so I've clicked on a cell in Paris here. And what this tells me is that those 10 hottest days, the average temperature of those 10 hottest days in an average year at this past warming scenario is 87 degrees Fahrenheit. In a cooler year or a 10th percentile year, those 10 hottest days may average out to be 82. And in a warmer year or a 90th percentile year, they may average out to be 95. So let's work through the warming scenarios here and see how this changes. And I want you to look at not only how the average changes, but how those cooler years change and those hotter years change as well. So we get a sense of not just how the kind of typical outcome is changing, but how the extremes are changing as well. So 1.5, 2, 2.5, and 3. By 3 degrees of warming, that those 10 hottest days on average are something like 10 degrees hotter. So that means that we're seeing very high temperatures in those 10 hottest days. And the very specific and quite old infrastructure of Paris will need to be prepared for that, as will the people who live there. So now moving on to a location that does tend to have very high temperatures. We're looking at the kind of border between Pakistan and India here in Hyderabad. Last year, actually probably close to a year ago, we were seeing really high temperatures in really early in the season in this area. And the thing that we need to think about as far as increasing temperature, especially in this region, are these high wet bulb temperatures. So we're looking at a map here of the number of days above 30 degrees wet bulb, so 30 degrees and 100% humidity. And as you can see in a past climate, this is something that generally just didn't happen in this place. It was unprecedented in a past climate. So let's work through the warming scenarios here. Now, at 1 degree of warming, we're seeing a couple of days a year, or in a really hot year, even up to a week of these very high temperatures. 1.5, 2, 2.5, and 3. So these are really significant changes now by 3 degrees, potentially a month a year at these very high heat and humidity temperatures, when it was something that didn't happen before. I mean, India in particular has gotten better over time at dealing with extreme heat. So they do have a lot of skills and tools to be able to put to this. But we need to use those skills and tools and think about how they can be applied towards something that is completely unprecedented and that we haven't experienced before. All right, moving to North America here, we are looking at Las Vegas, a place that I think probably everyone around the world has heard of, knows of. Las Vegas is in the middle of a desert. So what powers all of that energy, all of those bright lights of Vegas? What source of water helps those people and those farms around there to be able to have that big society there in Las Vegas? Well, it's this lake right here, Lake Mead. So this is where the water source for the entire region comes from. But Vegas is in a desert. So where does the water come from for Lake Mead? It doesn't come from precipitation in this place. I'm showing a precipitation map, and it's generally grays around here. Well, it comes from upstream. It comes from the Colorado River, the headwaters of which are in Utah and Colorado. So I'm selecting a place here that's upstream of Lake Mead here. I'm looking at a map of change in snowy days. So the cell that I've selected here is in the mountains of Utah. I've opened the baseline details. So what this tells us is that in a past climate, in an average year, this place would see something like 54 days where the conditions were right for snow. At 1 degree of warming, we're seeing about a week shaved off of that amount. I'll work through the warming scenarios here: 1.5, 2, 2.5, and 3. So by 3 degrees of warming, half of the snowy days are disappearing from this particular place. And as you can see, it's not a cherry-picked cell here, but the trends around all of these other places that feed into Lake Mead and many other places in the Southwest United States are going to see less snow, and as a result, less snow melt, and kind of not as stable patterns as far as water resources goes. All right, so moving on, I'm just going to take a brief detour here and tell you about a tool that we've developed alongside Probable Futures that we call Probable Futures Pro. And what this does is it gives a user the ability to bring non-climate information in and put it on the climate information. So this is part of this approach of making tools and skills available so that people can explore for themselves in their own communities how these climatic changes are going to intersect with the human built world and our human systems. So for example, here, I'm bringing in a data set from WRI looking at the power plants all over the world. So each one of these blue dots is a power plant somewhere in the world, put on top of the days above 32 degrees map. And I can start to kind of filter and change the data to start to give me a sense of how things are going to be changing and what is the intersection of power generation and a changing climate. Of course, we are trying to transform this power infrastructure, but we need to understand the resilience or the vulnerabilities of that power infrastructure to be able to do that well. So I can tell it here to show me the different fuel sources of the power plants by color code, which I've done that. I can tell it to scale the size of the radius to show me what the capacity is of that power plant. So it gives me the ability to start to hone in on these areas of risk and analyze them spatially, visually, numerically, and otherwise. So we are at a point where we're testing this right now, and we've kind of built a community of alpha users of this tool. So if anyone here is interested in playing around with this, please do reach out and I'll give you access to it. All right, so moving on, these maps make it really clear that life under a changing climate is going to be different, right? But the ways in which our lives will be different is completely and totally up to us. So what we have now, given the science that we have at hand, is an opportunity to imagine and design a future that both works with that new paradigm of a changing climate that we're in, whether we like it or not, and that limits the rate and the extent of that change. And this is a bit of a shift in thinking, because in the media and in public discourse, we often hear two binary views of the future. One where climate change is magically solved and the world is essentially exactly the same, but we have more electric cars and modern architecture. And then there's one where it's like perpetual apocalypse. And there's even a debate, an ongoing debate in the climate community and in other communities about optimism versus doomerism, right? Like we've all got to pick a side, as if those are the only two ways to think about a massive, complex, global scale problem that touches everything. We've really got to get away from this reductive thinking. We can choose clarity over anxiety. And that's because number one is no longer possible. We are already experiencing change, and we will continue to because of how much warming is baked in the system. And number two, that apocalypse is totally avoidable and a very far ways off. So what's the most useful thing to do now is to populate what those probable futures in between might look like. And we can use climate science as the constraints for that. We can make those that imagination be really well informed by what we understand about how our physical world works. So we can use science to tell stories that have bounded imagination. And those stories could explore how we live well under the realistic constraints that the earth and the climate give us. And there's really no constraints to where these stories can be told. We make assumptions about the future every day and incorporate it into our lives and routines. Those are stories. So we can incorporate these new stories and this kind of thinking into our annual budgets and strategic plans and white papers and family meetings and friendly conversations. I don't think I have to tell you all this. You're here for a reason, but everyone has a role, has a unique role to play in this climate challenge. Everybody eventually will be working on climate change directly or indirectly in some way, shape, or form. And I'm so grateful that you're all here for the challenge, and I can't wait to see the kinds of futures that you all imagine. So happy to answer some questions from here. And also, would love to hear how any of the questions that came through the lab yesterday too.
Thank you so much, Allison. We're grateful you are here as well. Thanks for sharing this with us. There are a number of questions in the chat, and I don't know if you'd like to just review that, have me read them out, or maybe we could call on folks to ask their questions verbally.
Yeah, I think if you could read them or if people could ask them.
Yeah, so maybe Balaji, I might call on you. You've got the first question in here about uncertainties and error bars. Would you like to unmute and ask that question?
Yeah, sure, Greg. So I see that you were showing maps with information about different metrics like temperatures, precipitation, and how they change with different scenarios. How do you capture uncertainties in a map like that?
Yeah.
How is that included?
That is the reason for showing the three different measures there. So what the climate models do is they simulate. So at a certain atmospheric warming, they simulate they simulate years essentially. They say, okay, at 1.5 degrees of warming, I'm going to simulate what might happen in a year, given everything that we know about Earth system dynamics. And so there are lots of different outcomes that come out from those simulations. There are actually 126 simulations behind each one of those cells. And so what we do is we show the average of all those simulations, so the average year, and then we also show the 10th percentile and the 90th percentile to give a sense of like the more mild outcomes that the simulations show, and then the more extreme outcomes. Now, outside of that, there's still 20% of those simulations that we don't show at all. And the reason for that is because they are extreme. So we don't want to kind of over index those extremes, but just really give a sense of the trajectory and the range. Those are the two most important things to understand when we're using climate information, is what direction we're moving and how are the extremes changing. One of the things that we try really hard to get through on the platform and in our speaking is that, I mean, first of all, these are they're models, they're projections, they are not predictions of the future. So they can help us have a sense of what's coming, but we shouldn't be relying on them to the point of, multiple decimals. That is not how climate information works, and that's not how we should be using it. So I didn't show it, but there's a whole portion on our site under the science tab where you can learn a lot more about this, and that gives people a bit of an education for kind of like data hygiene for using climate models, because now, we're moving into the general public using this information. We as Probable Futures are encouraging the general public to use this information. So we want to make sure that we have kind of a user manual with that to help people understand what are the grains of salt I should take, what are climate models good at, what are they not good at. So hopefully that answers your question.
Yeah. Thanks, Allison. I'm just going to go through the list of questions in order because I won't be able to track if I don't do that. So Sasha asked, on the wet bulb scale, it looked like the most extreme category was 30 out of 365 days a year. Is 30 days a year the threshold beyond which a place wouldn't be habitable? And Sasha, if you have anything to add to that, please feel free.
So that's not for me to say what's habitable and what's not. You know, this is the point of making this information available, is that we get to think creatively about how we may be able to live or not in those kinds of conditions. There is a bit of scientific debate around what the lethal combination of what that lethal wet bulb temperature is. So a lot of scientists have said 34 or 35 degrees Celsius and 100% humidity is a temperature at which a healthy adult sitting in the shade with a light breeze would not be able to survive after 4 hours, because at some point your temperature just keeps getting higher and higher. So there very much is a biological, a human threshold for what we can survive. But as far as like what places will pass those thresholds, I don't know. That is to be seen, and for I think us all collectively as a global community to figure out.
Yeah, thanks, Alison. And to add to that, if you recall, Dr. Chip Fletcher talked about wet bulb a bit and how places are becoming too hot for people to be outside. And if you think about your local context, how much manual labor is going on outside there? And if it's too hot to actually even survive outdoors, what does that mean for your local context? And hopefully that's sort of in line,
And
Alison.
play too. I mean, there's work and there's play. You know, play happens outdoors, and it's one of the wonderful things about being human is being outside and enjoying the world and playing. So, I mean, the other thing that I would say is that these lethal temperatures, I mean, we need to start thinking about these high wet bulb temperatures way before we get to, you know, these lethal temperatures, because these high wet bulb temperatures, even when not lethal, are still dangerous and uncomfortable. And so that changes the way that we live.
Thanks. And yeah, Kate had a question here. How do the leaders you work with typically react to these tools? How do you support them moving through the fear response and direct them to solutions? And Kate, feel free to add to that if you'd like.
Nothing to add. I think you summarized it.
Great. Thanks for the question. We've been presenting versions of this material for quite a few years at this point, and the reason that we're still doing it is because we see it work anecdotally, and we do get some information back from users of the site that it is effective. And I think you used the right word there, which is fear, which is very different from anxiety. Those are two different things. Fear is something that you can name, you can point to the source of it, and you can do things to protect yourself against those fears. Anxiety is like a general thing that just kind of hangs over your head and makes you feel bad. When I said we can choose clarity over anxiety, that is the approach here, that instead of just feeling generally afraid and anxious about what may or may not come, we can use the information that we have at hand and do the best that we can to plan for it and protect against some of these things. So the leaders that we talk to generally respond to that, that says to them, okay, there's something that I can do here. So what we do after that, it really depends on the community. In some cases, we just orient the leaders and get them thinking in this way, and then they go off and there's a whole, of course, you all know, a whole ecosystem of nonprofits, for-profits, people that can help once you're ready to get started on reducing emissions and building resiliency. But you need to get started with the right mindset. And that's really the space that we fill. So in some cases, we will continue to work with them. So an example is there's a supply chain risk software that our services company that the majority of multinationals, anyone with a big complicated supply chain would use this this software or something like it. They're starting to bring in probable futures data into that software and building it around, building the functionality around the needs of that particular community. What questions is that community trying to answer? And so we're working with them and helping them figure out how to do that, kind of bringing our expertise in, they're bringing their expertise in about supply chains, and we're building it for this particular group. But in other cases, we sit down with people who run very large companies and have a very public voice, and we get them oriented and they go off on their way, and now they're speaking very differently about climate change, and that's just as important. All of those things need to happen.
Along those lines, Simon had asked, is this data mainly used for adaptation or to encourage mitigation? And I think you've touched on this, but just maybe go a little further.
Yeah, both. I mean, I think it can be used in a more, it's used in different contexts. So it certainly is used in the context of planning for resiliency and adaptation. But there are, people using the maps, including us, to help get across the idea that we cannot adapt our way out of some of these warming scenarios. I mean, looking at the maps really does give you a very visceral sense that that is the case, that there are some of these warming scenarios that we just need to prepare for because we're very highly likely to live in those worlds and we need to be prepared for them. And some of those warming scenarios that we just want to avoid. And we have found that actually, in many cases, entering the conversation from that climate risk perspective and entering the conversation talking about adaptation ends up at mitigation. You're going to end up at mitigation at some point. We can't just continue living like this because we will, we'll break through limits. So a lot of the educational material outside of the maps on probable futures is about these limits and understanding where they are and what we need to stay within.
And that question came from Simon, and I see Simon has his hand up. Simon, did you want to add something?
Yeah, thanks, Greg, and Alison, thanks for a great presentation. It's super interesting. I work in healthcare, and it's a very interesting adaptation space, a kind of healthcare strategy. I guess I was interested in how you overlay data here to show, I guess, for so what. So, it's easy just to look at the temperature in itself from a drought to think, well, that's going to affect everyone the same. As we clearly know, poverty and land use and food sources, all of those, and underlying disease prevalence all play a big role in actually how these factors are going to impact on people's lives. And I worry slightly when I look at this data itself, that it underplays the issue and people think, oh, well, it'll be a bit hotter, I'll deal with it. And I just wondered how you bring in that nuance.
Yep, that's exactly why we built the Probable Futures Pro tool, and why I shared that today, and also why now that we've built these resources, our approach now is partnering with different organizations in different industries to then do some of those things that you're talking about, because climate change touches everything, every industry, every sector. And so we are not going to be able to have that expertise to do those overlays on every single aspect of life. What we can do is make these tools available and help these communities be able to do that. So for example, we have conversations going right now with a really big social service organization that's worldwide, but certainly US centric, to start to look at their communities and start to kind of overlay some of these data sets that you're talking about. but we need those people who are, people from healthcare, people from business, people from supply chains that can bring in that expertise. And so we can do more of that work. So that is really the phase that we're in now. You'll start to see kind of more reports and partnerships and that sort of thing come from Probable Futures, the things that we publish from here on out, but we've also made this tool Probable Futures Pro available so that anyone can come in and start to do that work on their own.
Thanks, Allison. Charlotte asked a question in the chat a while ago. Would be curious to know how you respond to questions like, if it's only 2 degrees warmer, why are the hottest days hotter? Basically, how do you help people grapple not only with the mean, but the variance that's part of this future?
Mm-hmm. It's a good question. And our approach is the maps is just showing that, at this level of warming, this is how things change at a local scale. Also so the educational material that leads up to the maps gets into a lot of this too. So like helping people understand just how the Earth systems work. So starting with things like the greenhouse effect. That's a very effective metaphor. And it does help you to, some understanding of Earth systems and how they work is necessary to understand the maps, which is why we built that material around it. And it's not, it's not rocket science either. It's all things that a lot of people learned in elementary school even, or middle school. And we just haven't had to use it for a long time because we've lived in this, been lucky to have this climate stability. And now that we're moving into this less stable paradigm, we're going to need to use our understanding of Earth systems a lot more.
Great. Thank you. There are a bunch of questions here about target market, target audience. Are you working with media? One question in particular was, what is the software you were talking about, logistics software? Do you know the name of that? Or is it?
But I can't share it yet. But pretty soon I'll be able to.
Okay, great.
It's not public yet.
Yeah, go.
Okay, so target audience so there's 2 kind of different aspects. There's Probable Futures, the digital climate literacy platform, and then Probable Futures, the organization, and what we're doing from here. The intended audience for the digital climate literacy platform is as broad as possible because everybody needs to understand this. This relates to everyone in some way. So we made the conscious decision to not specify a particular target audience for those materials and to make it as accessible as possible. We'll be taking another step towards that this year in translating the site. So you can expect that to come in the future. But then as an organization, where we are focusing to help people and organizations use and apply these tools is across different industries. So it's not picking a particular industry. Again, every industry, every sector needs to deal with this, but we can identify places where learning is happening on climate change, or where people in organizations are just getting started. So we tend to get involved with organizations when they're at the very beginning of their journey, and that is actually how we target. So it's not a target audience that is kind of like recognizable, saying, we're only working with business people, or we're only working with social justice organizations or advocacy. We're working across those boundaries, but with organizations that have basically signaled a willingness to get started and are interested in learning. So
No.
an example of that is this. That is why, you know, I am doing these talks every month. One of the reasons is to connect with people like you, but you have all self-identified as wanting to understand climate change more. And so that's a pretty good target audience to start with. We want people to get started with a really good foundation. People around the world know a lot about climate change, but that doesn't necessarily mean they've had an education on climate change or have like a real organized way to approach it. So that's really where we're targeting.
Great. And is it Manj?
Yeah. Hey, Greg. Sorry. So Alison, great presentation. I'm a big fan of big data. So would you say that it was like more of a consulting approach that you would take? Like, let's say there's company X, right? And that's looking at an ESG strategy, and then they're looking to understand the data sets around the world of their operations and how it could have an impact, and how the temperature increases or the precipitation increases or whatever that would have an impact. So would we say like it's more of a consulting approach that your organization's doing for these bigger, larger corporations?
Yeah, I guess you could call it that. I mean, that is what we're doing, is advising and consulting and teaching within these different organizations that are not just corporations, but are educational institutions and advocacy organizations. But everything that we do is non-commercial. It's a completely philanthropic initiative. So there's no transactions that happens. So all of the consulting that we do is pro bono, and we choose the organizations that gives us the ability to choose the organizations that we work with, and choose the ones that we think have the most opportunity for leverage and the biggest ability to then disseminate this information and this way of thinking through their community in the way that kind of works for their community.
Awesome. Thank you.
Thank you.
And thanks, Alison and everyone. We're pretty close to the end of our time here. There are a number of questions, Alison, about how people can access the maps and the data, how they could be in touch with you, and how they could become beta users or get involved with that pro system you talked about. So if you wouldn't mind touching on that really briefly, and then thank you so much.
Great. Yeah, just feel free to reach out to me. My email is asmart@probablefutures.org. You can also find me on LinkedIn. You all are also very lucky to have a special person in your cohort who is part of the Probable Futures family, Isis Dallas. So I won't volunteer her for too much, but she knows how to get in touch with us and knows a lot about what we're doing too.
Thanks, Alison. And as usual, I will reach out and ask you if we could get a copy of your slides, and I'll share those with the fellows as well. And glad to know, Isis, that you're with Probable Futures. I may have some questions for you as well. So thank you, everyone. Thanks so much for joining us. Thank you, Alison, for a great talk.
Thanks so much, everyone.
Thanks, Alison.
Goodbye, Al.
Thank you.